We are very excited to have Sidhanth Mohanty with us as a guest speaker. Sidhanth is currently a postdoctoral researcher at MIT, where he is hosted by Sam Hopkins. Earlier, he got his PhD from UC Berkeley, where he was advised by Prasad Raghavendra. He is generally interested in algorithms and complexity in the average case and in the area of spectral graph theory. Today, he has very kindly agreed to give this talk on his exciting recent new work on locally stationary distributions. So with that, I hand over to Siddhant and take it away.
Yeah, thank you for inviting me here, Ramesh, and thanks for the introduction. Yeah, I'm very glad to be here. And today I'll be talking about locally stationary distributions, which is based on joint work with my wonderful collaborators, Kwee Liu, Prasad Raghavendra, Amit Rajaraman, and David Wu. Kwee is a professor at MIT. Prasad is a professor at Berkeley. Amit is a first year PhD student at MIT, and David's a second year PhD student at Berkeley. Okay, so now I'll dive into the technical part of the talk. In the setup, think of mu as being a probability distribution and think of it as being high dimensional. So, for example, on the Boolean hypercube or in high dimensional Euclidean space. And a common algorithmic goal that occurs a lot of times in the study of algorithms is to sample from such high dimensional probability distributions with an efficient algorithm. And now the reason people care about this algorithmic primitive of sampling from a distribution is because it has a bunch of downstream applications. For example, sampling from certain distributions can help you solve optimization problems. Um, it's a routine that comes up a lot in Bayesian inference. And it also shows up when you're trying to, say, integrate functions or compute the volumes of bodies. So sampling from a distribution is a pretty important primitive. Um, and since it might be a little bit abstract to think of mu as a generic probability distribution, let me give you guys a couple of examples to keep in mind throughout this talk, since the results will be oriented towards these probability distributions. So the first example is what is known as the hardcore model for independent sets. So you have a graph G. You should think of the graph as having some large number of vertices, n vertices. And then there's an associated parameter, lambda, which for physics reasons is called the fugacity. And now you should think of the distribution mu as being associated to independent sets on the graph G. And in particular, for an independent set I, you sample it with probability proportional to lambda to the power I. So just to get a sense of what lambda is doing, if lambda is equal to 1, then you're weighing every independent set the same amount. So this gives you the uniform distribution on all of the independent sets. And when lambda is larger, think of it as being a huge number, then actually all the probability mass is going to be placed on the maximum size independent sets in the graph. And yeah, I guess the smaller lambda is the more you favor smaller independent sets. So okay, like I just mentioned, as lambda goes to infinity, it's supported on the maximum independent set. Now, a second class of problems that also gives us distributions that you all should keep in mind is a probability distribution that comes up when you're trying to solve constraint satisfaction problems with a planted assignment. So to be concrete, once again, let's say you have a graph G, and then there's a hidden signal vector, which I'll call X, which you should think of as being sampled from the n-dimensional Boolean hypercube. Here, n is the same n as the number of vertices in the graph G. And then you're given as input for every edge in the graph, you're given say the edges between endpoints I and j. You're given a measurement as to whether the two endpoints have the same value of x or a different value of x, but like a very noisy version of this measurement. So concretely, associated to each edge ij, you're given a plus minus sign sigma ij, which is equal to the product of xi and xj with probability a bit larger than half, and it's equal to minus xi, so you have probability a bit smaller than half. And now, once again, once I give you these measurements, sigma ij, your goal is to recover x, and a natural algorithm to try to recover x is to try to sample from the posterior x conditioned on all the sigma ij's. So basically, try to apply Bayes' rule on this distribution, since I told you what the general process is. And a nice fact is that this posterior distribution of x has a nice succinct description, and I've given a formula for what it looks like. I guess it's known as an Ising model, but if Ising model doesn't mean anything to you, don't worry about it, because you won't really need to know it for the rest of the talk. And by the way, if people have questions, you should feel absolutely free to unmute yourself and ask me. Okay, so far, I guess I motivated the question of sampling from high-dimensional probability distribution and gave two examples. One arising from solutions to planted CSPs, and another arising from independent sets in a graph. Okay, so now that we've motivated sampling from distributions, what is the algorithm of choice for sampling from a distribution? So there's a very versatile algorithmic framework called the Markov chain Monte Carlo framework. And it's based on the following principle. So you want to sample from mu. So what do? You design a Markov chain whose stationary distribution is mu. And then you simply initialize somewhere and then run this Markov chain for some large number of steps, some t steps. And then in the end, you want to output xt. And okay, I guess before I proceed, I maybe want to say why one actually runs a local algorithm like a Markov chain instead of using a more global sampling technique. So in all of these high-dimensional distributions, like on the Boolean hypercube or independent sets in a graph, actually the number of elements in the support of this distribution is exponentially large. Like there's exponentially many independent sets in a graph. There's exponentially n many vectors on the hypercube. So you can't simply go over each individual element and compute a probability. And instead, you necessarily need an algorithm that's more local. And a Markov chain which simply takes a solution and edits it a little bit is the algorithm of choice. Okay, so you would hope that even though you ran this Markov chain on this exponential size space for only polynomial and dimension many steps, it converges to the stationary distribution. And in many cases, it does, and it's a topic of pretty intense study. So again, let me go over a couple of examples that are relevant to the distributions that we discussed. So let's once again revisit the hardcore model and describe a Markov chain to whose stationary distribution is the hardcore model distribution. Okay, fix the value of lambda as 1. So then the target distribution that you want to sample from is a uniformly random independent set in the graph. And here's a simple Markov chain whose stationary distribution is a distribution of independent sets. So start with the empty set. Well, the empty set has no vertices in it and is vacuously an independent set. And now each iteration of the Markov chain is the following. You choose a random vertex, V. Now, if there is a neighbor of V in the independent set that you have so far, then there's no chance V can be in the independent set. So you don't do anything. You just say, okay, well, like nothing happened. Okay, but then if V has no neighbors in the independent set, then there's some chance of V being in the independent set. And in particular, if V is already in the independent set, then you flip a coin and remove it with, if the coin comes up heads, in particular, you remove it probability half. And if V is not an independent set, you add it back with probability half. And here's just like a run of the Markov chain for 3 steps, just to give you all a sense. So here the vertices that are highlighted in green are the independent set that I have at a certain time. And now I choose this red vertex that is circled in blue. Now this red vertex has at least one neighbor, which is in the independent set. So you just do nothing. Okay, then you resample another vertex. Now you sampled this vertex here at the bottom, which is in the independent set. So you erase it with probability half. Okay, and then you did in fact happen to erase it, and then on your next step you encountered this vertex at the very bottom, and you add it with probability half, and so on. So this Markov chain is called Glauber dynamics, and is a well-studied Markov chain for this problem of sampling from the Markov model. Okay, I'll pause to see if people have any questions, because this is maybe an important junction. Okay. Okay, so concretely, what is the notion of a mixing time in a Markov chain? It's the time taken by the Markov chain to get epsilon close to the target distribution in total variation distance. So I'm going to call the epsilon mixing time for being initialized at x as the smallest time at which t steps of the Markov chain initialized at x is epsilon close to the target distribution mu. And if we can show that a Markov chain mixes in polynomial in n time, then we're happy. We have samples from the distribution, and then we can do whatever we want with the samples. Okay, but now let me throw a curveball at you. I said all these things about how it's important to sample from distributions, but and then you run Markov chains to sample from these distributions. But one interesting phenomenon is that there's many Markov chains whose goal is to sample from a distribution, and these Markov chains actually fail to mix fast. But even though they fail to mix fast, they are actually empirically still successful at the downstream task of sampling. So they might be failing at solving the sampling problem, but they're still actually pretty successful at whatever you wanted to use sampling for. So as an example, once again, this planted CSP example that I gave, which I guess is a specific case of the 2XOR instance. If you run the Markov chain when the graph is random, then it actually empirically finds the planted assignment in a small number of steps. And okay, I guess even outside of the stylized model, from the early 90s, there's a work on SAT solvers and CSP solvers that people use a lot in practice. And the early SAT solvers were actually based on running a Markov chain. And okay, like SAT is a crazy problem, SAT hard. Like probably when you run a Markov chain, even on like some crazy real world instance, you're probably not going to be sampling from the distribution, but it nevertheless is pretty effective at finding good solutions. And
Siddhant,
in fact,
I had a question. So when you say that Markov chains fail to mix fast, do you mean that we are unable to show that they mix fast, or do we know that after any polynomial n steps, the TV distance is still large? What do you mean by?
actually in these scenarios, they actually fail to mix fast. Like the second thing that you said, after you run it for polynomial n steps, the TV distance is still pretty large, maybe even pretty close to 1.
Okay. Yeah.
Right. Yeah. Okay. So I guess so one theorem that we can show in the context of 2XOR like problems is that running a Markov chain actually recovers an assignment x hat, which is correlated with the planet assignment x, even though this Markov chain itself fails to mix fast. And okay, you need some assumptions on like what this parameter epsilon is and what the degree of the graph D is, and you need the graph to be random. But okay, in some somewhat stylized setting, we can explain this phenomenon that is being observed empirically. Okay, and now here's a second example which I think should maybe give a more satisfying answer to the question that Ramesh asked. So if you consider this Markov chain for sampling a uniformly random independent set that I showed a few slides ago, it actually also fails to mix fast. Not only does it, uh, and it fails to mix fast when D is greater than 6, but not only does it fail to mix fast, sampling from this distribution is an NP-hard problem. Uh, and even if you make an assumption like the graph is triangle free, which is very striking because, okay, I defined the sampling problem and I said, hey, here's my algorithm for the sampling problem, which is running a Markov chain. And this Markov chain happens to fail to mix fast, but then you might just think, well, the Markov chain might just like not be a great algorithm. Maybe you should be doing something else. But no, actually, if you can sample from a uniformly random independent set in the graph, then NP equals RP. So okay, but the point is this is a very hard problem. Okay, but now let me say something. First, a fact about why one might care about this problem of sampling a uniformly random independent set in a graph. And then I will say something about the Markov chain. So in the 80s, it was proved by Aitai, Kamlesh, and Semiradi that when you have a graph G, which is deregular, and this graph G also additionally has no triangles in it, then there is an independent set in the graph of size n over d times log d. So an independent set of size order n over d exists just because the graph has all degrees bound by d. But if you additionally know that it's triangle free, then you get this extra log d factor. And there's a proof of this statement in the probabilistic method book of Alone and Spencer, where they show that in fact, if you choose an independent set uniformly at random, then the expected size of this independent set is the thing you want, this n over d log d quantity. So, okay, so if you could sample a uniformly random independent set, you could find an independent set of this n over d log d size. But like we just said, the sampling problem is hard. But actually, what we can show is, nevertheless, if you run this Markov chain, whose goal is to sample from the uniform distribution, even though it fails to sample a uniform independent set, it nevertheless still finds an independent set of the desired size, omega n over d log d. So I guess this is like an example of when you care about optimization, finding a large independent set. Um, a sampling algorithm would have helped you do it, but even though you fail to sample, you still succeed at optimization. Okay, so I'll let people absorb this for a second before moving on to the next phase of the talk, which would be dedicated to how we analyze such algorithms. And I'll pause to see if people have questions. Okay. Okay, so I guess the title of this talk had this word locally stationary distributions. So now I finally get to tell you what a locally stationary distribution is and how one uses it to analyze slow mixing Markov chains. So okay, say P is some Markov chain. Now here I've made a plot. On the x-axis of this plot is time. So you're just like initializing this Markov chain somewhere and running it for a long time. Okay, so the x-axis is time, and the y-axis. So okay, think of nu t as being the distribution that you're at after running t steps of the Markov chain, or running the Markov chain for t time. And think of f of nu t as being the distance between the distribution nu t and the target distribution mu. Okay, and now concretely, if you want something concrete to think of f as, you could think of the TV distance, or you could think of the KL divergence, or the chi-square divergence, whichever one. But one key aspect of this function f, which is measuring the divergence between nu t and the target distribution mu, is that it actually is a monotonically decreasing function of time. As you run the Markov chain for longer, you never get further away. You can only possibly get closer. Maybe you don't get closer at a quick rate, but you never get further away. And one immediate upshot of the fact that f is monotonically decreasing in time is that if you look at the derivative of f with respect to time, then it's going to be small on most of time. Okay, I guess let me just make a more concrete claim. Let's say capital T is some time that you choose that you're willing to run the Markov chain. So think of capital T as being polynomial in the dimension. So maybe think of capital T as being like n to the 20 or something. And then what you do is you choose a random number between 0 and n to the 20, and you run it for that number of steps. Then the claim is the distribution that you reach after you run it for little t time has this property that the divergence between the distribution and the uniform, or not uniform, and the target distribution mu is pretty small in magnitude. So this number is always negative, but it's never too negative. It's only going to be as negative as the initial divergence divided by t. So it's going to be something divided by n to the 20. And the way to see it, you can basically see it from this picture. Like here you have some function. You have a curve that starts off at some number and is only possibly decreasing. And if it's decreasing at a steady rate, it's going to hit 0 at some point. But if it doesn't hit 0, it means at some point it stopped decreasing as fast. That is, this particular derivative quantity was small in magnitude. So this motivates the definition of a locally stationary distribution as a distribution where this derivative of the divergence with respect to time is very small. That is, the distribution is not making progress towards being towards the stationary distribution. And okay, now this is a sort of abstract definition because okay, I said f is a TV distance chi-square divergence or KL divergence, but maybe let's for certain concrete f see look at what this derivative quantity is, because we would like an interpretation for what it means for this derivative quantity to be small. So when you have the chi-square divergence, actually the derivative ends up having a pretty nice form, and and in particular, let me just like unwrap what this form is for you. So you choose a random x according to the true stationary distribution mu, and you choose a y which is a neighbor of x. Okay, so now here it's saying that nu of x divided by mu of x minus nu of y divided by mu of y is the average square of this is small. That's what it means for the derivative of the chi-square divergence to be small. So the way you can interpret this is this distribution nu you reach has a property that if you choose a random point x, in the neighborhood of x, it's proportional to the true stationary distribution mu. And okay, I guess some of you might recognize this quantity as being the Dirichlet form of, so it's like, think of the vector in the which is defined by the ratio nu over mu. And basically the derivative of the chi-square divergence is the quadratic form of this vector against the Laplacian of the graph. Okay, so here's here I just told you that local stationarity is defined as some particular function associated distribution being small. But let me give you a more pictorial viewpoint of how you should think of a locally stationary distribution. So here's a locally stationary distribution. So here, in this picture here, I've made a depiction of the state space omega. So you should maybe think of this box as being the hypercube. Okay, so in a locally stationary distribution, you can partition the state space into a bunch of pieces. So I guess we can call each piece a cluster. So there's a bunch of clusters, C1, C2, up to CL. And the locally stationary distribution has two properties. If you zoom into any individual cluster, let's say CI, then the distribution nu conditioned on falling in CI is actually the same as the true stationary distribution mu conditioned on falling in CI. Okay, but this condition alone is maybe not actually a strong condition, because you could imagine a trivial clustering where each state in the Markov chain is its own cluster. So the second condition is what makes it non-trivial. So if you sample X according to nu, well, you fall in one of the clusters, and then you choose a random neighbor of X according to the Markov chain P, then actually with high probability, X and Y would lie in the same cluster. The probability that X and Y lie in different clusters is pretty small. It's less than epsilon. So in some sense, what this is saying is you can you should intuitively think of a locally stationary distribution as being a collection of disjoint clusters, and the cut between any pair of clusters is very sparse. And within each cluster, you look like the stationary distribution. Okay, so this is like the intuitive picture for the locally stationary distribution, and I'll show why this is a useful notion in the next part of the talk.
So Siddhant, this distribution being a locally stationary distribution, this doesn't depend upon the distance function that you're choosing, the TV distance or chi-square, does it? It doesn't depend upon that then.
Okay, so I guess this intuitive picture that I gave does not depend on that. You're right. But okay, like in the previous slide, I did say I call something. So okay, thing is, I would actually want to choose a KL divergence here, but I intentionally made it generic so that I guess I didn't want the choice to make it seem like it was important.
Okay. But
Yes, but like, actually formally we define it using the KL divergence.
okay, but their distributions under some distance metric, they are not locally stationary, and under a different divergence they are stationary,
Yes,
locally
so this
stationary.
is actually entirely possible.
Okay.
So okay, yeah, like no, that's a very good point. So this particular clustering picture you should think of as happening when it's locally stationary under the KL divergence.
Okay. Yeah, thanks, sir.
Yeah. Okay.
So one question. So this second condition here does that hold for all X, or is that for a random X?
Yeah. So the second condition is only for a random X according to nu.
Okay.
Yeah, I guess okay. Actually, when I must say, like when I state this, this is not like necessarily a totally formal thing that we proved, but I think it's maybe more so an interpretation of like what should be happening. Okay. And any other questions? All right. So now I defined what a locally stationary distribution is for you, and why is this a useful notion? So we'll see one instance of a sort of meta principle, where if you have a proof that sampling from the true stationary distribution mu succeeds for some algorithmic application, and if you can verify that the same proof only uses local stationarity instead of like full stationarity, then you automatically get an efficient algorithm via running a Markov chain. Okay, so that was abstract. So I guess I will. I'll explain what I mean in the context of finding independent sets of size n over d times log d. That is, we're going to open up the proof that Alon and Spencer gave that a uniformly random independent set in expectation has this omega n over d log d size. And then we're going to observe that actually the Alon-Spencer proof goes through even if instead of the uniform distribution, you merely had a locally stationary distribution, which would then imply this theorem that running the Markov chain finds an independent set that is of this n over d log d size. Okay, so let me just give you all a proof of this fact. So in this proof, let's think of x as being a n-dimensional 0, 1 to the n vector, and think of it as being the indicator vector for the uniformly random independent set that was drawn. So ones in the entries which are actually in the independent set and zeros everywhere else. So now the size of the independent set is given by the sum of all xi's. Okay, so now for the sake of this proof, we're gonna count the size inside the independent set in a slightly different way. Remember, the graph is deregular. So I claim I can describe the size of the independent set using this function that's on the right. So I sum over all vertices I, and if the vertex I is chosen in the independent set, then I put a weight of d, and then I give a weight of 1 for every neighbor of I that is also in the independent set. Okay, so now I claim in this sum, I count every vertex 2d times. In particular, if this vertex I is in the independent set, then it gets a weight of d for the term I in this outer sum. And for each of its neighbors, it gets a weight of 1 in this inner sum. So any I in the independent set is counted 2d times. Okay, so the size of the independent set is 1 over 2d times the sum of these local functions. And I'll call these local functions the scores. So okay, the size of the independent set is 1 over 2d times the sum of the scores of all the vertices. Okay, I'll pause for a second to let folks absorb this. Okay, so now the expected size of a random independent set is 1 over 2d times sum of all vertices and the expected score of each vertex. Now what we're going to show is that the expected score of any single vertex for uniformly random independent set is larger than log d. If we show that the expected score is larger than log d, then actually observe that we would be adding log d n times. So we get n times log d over 2d, which was the size of the independent set that we actually wanted to find. Okay, but in fact, the proof is going to show something even stronger. It's going to show the following. So say you have a vertex I has a bunch of neighbors. And now, okay, I look at the graph outside of this purple dashed ball. So the vertices in the graph, excluding I and its neighbors. And if I think of having any assignment to the vertices outside this ball, I guess I'm calling the rest of this assignment X, rest of the complement of I and its union its neighbors. So if I have any pinning, and when I say a pinning, what I mean is for each vertex outside this ball, I determine whether that vertex is an independent set or not. And even after I condition on all of this information, and the only randomness I have left is on I and its neighbors, the expected score of I is actually still going to be at least log d. So I'm going to prove this stronger statement. So let's see why the stronger statement is true. Okay, so now say I fixed x outside of I and its neighbors. Now after I fixed x, there's going to be some neighbors of I which are forbidden. Like, for example, here I crossed out two vertices, and maybe they're forbidden because one of this dude's neighbors was chosen to be in the independent set. One of this vertex's neighbors was also chosen to be in the independent set. So these are forbidden. But then there's some number of vertices which are circled in green, which are not forbidden, which is they can still possibly occur in the dependent set. So let's say k is the number of allowed neighbors after I have fixed x outside of I and its neighborhood. Then actually, what is the remaining conditional distribution? What is mu condition on like the pinning outside of this neighborhood? It's actually simply a uniformly random independent set on a star graph with k leaves. And the k leaves are going to correspond to the vertices circled in green, like the ones which are still allowed. Okay, so now the expected score in this conditional distribution is the expected score if you were sampling a uniformly random independent set from a k star. So now let's just see what it is. What is a uniformly random independent set in a k star? The independent sets include either I choose the singleton set, which is given by the center vertex, or if I don't choose the center vertex, I choose a uniformly random subset of the neighbors of the center vertex, of which there's like roughly 2 to the k many subsets of the neighbors of the center vertex. Okay, so if I do choose the center vertex, this happens with probability roughly 1 over 2 to the power k. So the expected contribution of this d times xi part of the score is d over 2 to the k. But if I don't choose the center vertex, I'm choosing a uniform subset of my k neighbors. And the contribution of those, and you're going to choose roughly half of them. So the contribution of those is k over 2. Okay, now I claim for every integer k, this function here is always at least log d. Okay, maybe up to a constant. And okay, the way to see it is, well, if k was already as large as, say, log d over 2, then the second term alone, the k over 2, gives you an order log d. But if k was smaller than log d over 2, then the denominator here is not going to fully cancel out the d, and you're going to have some, enough left to make the first term larger than log d. I was being loose with the constants here. And okay, I think I realized I may have said a mouthful, so I will once again pause and see if there's questions about this part. Okay, I'll keep going then. Okay, so the conclusion of this part was that when I sampled a uniformly random independent set, I got a score of at least log d per vertex, and hence an independent set of size n log d over d. But now, how does this port over to locally stationary distributions? So let's look at this claim. The claim said, if I look at mu conditioned on a pinning outside of I and its neighbors, then the expected score of this conditional distribution is at least log d. And what we're going to show is if nu is a locally stationary distribution, then when you take nu and condition on a pinning outside of I and its neighbors, the conditional distribution actually matches mu condition on x pinned outside of I and its neighbors. So actually, when you have a locally stationary distribution nu, you could run through the same proof, and you'll have to show that the expectation of conditional nu of the score is at least log d. And because nu conditioned on the pinning outside of I and its neighbors, the same as mu conditional on pinning of I outside its neighbors, the proof that I just showed you also establishes this lower bound. Okay, so now the final technical portion is where I'll show you why a locally stationary distribution conditioned on a pinning is the same as the true uniform distribution of independent sets conditioned on the pinning. Okay, so here I've once again drawn the same picture, the same intuitive picture that I use for illustrating locally stationary distributions. So and now if you look at these conditional distributions, which are of the form nu conditioned on x pinned outside of I and its neighbors, these distributions are all supported on subcubes. And the thing you can interpret our proof as doing is in showing that most of these subcubes, namely the set of all x where most of the coordinates of x are fixed, completely live inside one of these clusters. Okay, so now if you completely live inside one of these clusters, then it means condition on being in the subcube, you are actually going to look like the true stationary distribution mu condition on being the subcube, because the only places where the locally stationary distribution differs from mu is if you have regions like this purple cube here that straddle between two different clusters. And now, how are we going to show this? So I claim it's going to be a consequence of the fact that if you look at the Markov chain P that we started with, like the Glauber dynamics Markov chain, the one that was whose stationary distribution was uniform on all independent sets. The claim is this Markov chain, restricted to each subcube, has good expansion. So okay, thing is, I said that the overall Markov chain is slow mixing. So the overall Markov chain is not an expander. Its expansion is really bad. It's like exponentially small in the dimension. But the claim is when you restrict it to these subcubes, it is actually an expander. And the reason is, well, when you restrict it to a subcube, then you saw star graph, and the star graph, like the uniform distribution over independent sets of star graph, the Glauber dynamics for that actually has good expansion. Okay, so now why is it the case that if a subcube is an expander, it has to live within a cluster? Oh, why can't it be the case that the subcubes straddle two clusters like this purple cube that I drew here? Okay, now the point is, if many subcubes did cross between these different partitions, between these different clusters, then you would be in violation of the second condition here, which is the fact that if you take x according to the locally stationary distribution nu and sample a neighbor y of x, you know that the probability that x and y are in different clusters is pretty small. But because these cubes are expanders, if these cubes were in fact in different clusters, the cuts between these clusters would no longer be sparse. These cuts would actually have a lot of edges due to the expansion of the subcubes. Which means the only consistent picture here is that the subcubes live within clusters. And because they live within clusters, the conditional distribution on them is the same as the conditional distribution on mu, and then the overall proof goes through. So I guess if one actually wants to implement this proof, you can do it like more analytically without ever talking about the clusters or like the combinatorics of sparse cuts. But I guess I thought that this intuition would carry over. Yeah. Okay, I see Anand has a question.
Right. So don't you need to do something a little stronger here? Because so right now what you're saying is that on average, most of these cubes are not cut, right? But your
Yeah.
global dynamics starts from a very specific starting point, say the empty set. So most likely you're really only contained in one of these regions, right? Say C1. So wouldn't you need to show this conditioned on specifically for the cube that you're most likely, the region that you're most likely to be contained in?
Okay. Yeah, I see what you're saying. So the thing is, you should think of the cubes here as being weighted according to the distribution nu that you reached. So I think you're right that if the statement that I told you is of the form most cubes when weighted by like the distribution mu were contained within clusters, then you might be in trouble because somehow you start somewhere, but then you happen to be in a region where all the cubes are bad. But I guess here I'm
Right.
saying
Yeah.
most cubes which are weighted according to nu, where nu is the locally stationary distribution that you reached when you
Right.
ran your Markov for a while, are actually contained within clusters.
Okay. Got it. Yeah.
Yeah. You know, a good question though. I think I was maybe not so clear about it. So thanks for asking. Okay, I'll wait to see if there's any other questions because okay, so I guess in summary, uh, what what we saw here is you had a Markov chain, which was meant to sample a uniformly random independent set. Um, it did not mix to its stationary distribution fast, but instead it mixed to a locally stationary distribution, which had some nice structural properties, uh, which made it so the conditional marginals of this distribution matched the conditional marginals of the true stationary distribution. And that was actually all you needed uh, for proving that you found a large independent set. So now I want to conclude with uh, two open questions that I'm interested in. So one of them is so I guess the first application that I mentioned to solving CSPs that was like an average case problem. So the question I want to ask is whether you can use this framework of locally stationary distributions to say that Markov chain Monte Carlo actually gives you good approximation algorithms for worst case optimization problems. And maybe a good starting point for this would be to check whether you can approximate max cut arbitrarily well on dense graphs. So in dense graphs, there's actually a polynomial time approximation scheme that's known. That is, you can get a 1 minus epsilon approximation for max cut. And the question is, can like a Markov chain Monte Carlo based method also do this? Because the current dense graph methods are either based on like uh, the regularity lemma or on rounding sum square semi-definite programs. Okay, and I guess the second question that I wanted to ask was so often in this like area of like average case planted inference, um, you tend to solve a bunch of these like planted constraint satisfaction problems with planted solutions using spectral algorithms or semi-definite programs. Uh, but is it true that whenever you have an algorithm that uses eigenvectors of a matrix or a semi-definite program, then actually a simple Markov chain algorithm also succeeds? And this would be interesting because these spectral and STP-based algorithms tend to be like a little bit more complicated, whereas uh, running these Markov chains tend to be like some simple local search type thing, which you can implement pretty easily with like 4 or 5 lines of code. So it'd be nice to say that in a sense, Markov chains simulate STPs and spectral algorithms, at least for average case statistical inference problems. And with that, I'll conclude my talk, and yeah, I'll be around for some more time for discussion and if people have questions.
Let's thank the speaker, and yeah, we are open to questions.
So what is the running time of this? Is it like n over epsilon or something? Yes.
Yes. Okay. So for the independent set result that I showed you, the running time is like linear in n times polynomial in the degree, and the polynomial that we have is like d to the 4, but I actually believe it should probably be like n times d time. And I guess for the planted inference, the running time is kind of bad. It's like n to the 4 or so. But again, for the planted CSP thing, you can like simulate it on a computer, and it seems to run in like basically linear time, I want to say, because I ran it on like instances of size 100,000, and it converts in like 300,000 iterations to a good solution. But yes,
No.
our analysis is like n cube.
No, I was asking like more generally. So is there like a bound on how many steps it would take to reach at this locally stationary point, or the function of saying?
Okay. So right, I think I can say something concrete about that. So let's go back here. So here, okay, here we said something like if you run it for capital T time, then your this derivative quantity is bounded in magnitude by the initial divergence divided by capital T. So now if you think of this function f as being the KL divergence to the stationary, then the nice thing about KL divergence is that it's always at most like poly n for most reasonable distributions. Like it's only going to be super large if there's like some really low probability things, but usually for things like independent sets and stuff, all your probabilities are lower bounded by like something exponentially small. So you should think of f as being like n. So now if you run t for say n over epsilon time, then you get to make this epsilon small. One thing I do want to point out is, I guess often when we do like Markov chains or spectral graph theory and stuff, we really like eigenvalues and the chi-square divergence. But the issue with that is actually because the state space is exponential in size, if you just start off at a singleton vertex, then this f of nu 0 can be exponentially large. So if you have like, if you're working with chi-square divergence, then actually t, at least using this maybe naive bound, t has to be exponentially large. But okay, I guess the short answer is n over epsilon time to get like epsilon locally stationary using KL divergence.
Okay. Yeah, and about this claim, so is it not true if we don't have the expectation here? Well, it seems like the rate of mixing usually just gets slower, right? Slower, right?
Yeah. So I was so yeah. Actually, at some point, like we were also wondering about this, and as in, is it the case that like the derivative itself is also monotone in time? So then if it's like small at some point between 0 and t, then it remains small. But there was some paper which, among other things, actually gave like a 3 or 4 state Markov chain, which is time reversible, but the derivative is not monotone. So,
okay.
So okay, I guess that was interesting. But I would still hope that. But it seemed like a very contrived and manufactured chain. So I would still hope that for like the natural kinds of things that we're considering, like global dynamics and so on, it should be monotone. Yeah, I don't know how to show it though.
Okay.
Okay, so do we have any more questions? Okay, so then let's stop the recording and let's thank the speaker again.
Yeah, thank you all for coming.